Understanding section 15.6 triple integrals is all about practice. You should do a lot of exercises. So I also decided to do more examples. I'm going to do 2 examples from that section exercises beginning with 10. We are given this region in 3D, the volume trapped by the red lines in my picture. So one of the faces, one of the walls is the vertical plane given by y equal x. Because z is not present in that equation, that means z is free parameter. And then the top part, the curved part, is bounded with z equal 4 minus y squared. And then the restriction is that we are above the z equals 0 axis, z equals 0 plane. So our job is to integrate the function f of x, y, x times y, over this region given here, D. How do we integrate this? As we know well at this point, is to first write it as an iterated integral. And the most difficult part is getting the boundaries of that triple integral right. In this picture, the easier way to parameterize would be to start with the projection on the xy plane, because it's a triangle and it's rather simple to parameterize it. And so we start here, it's pretty symmetric. We can start either with x or y. So let's see first where I'm going to do y, so from here to here. So when y ranges from 0, as you can see in the picture, up to, okay, where would that point be? We see that, well, it happens when z is equal 0. That means this surface hits the y-axis, and from this we get y equal plus minus 2, and the picture says plus 2 is the one. So plus 2, that will be the dy, the outermost integral. So as y ranges from 0 to 2, now I want to do the dx part. So what happens, that will together describe the projection. So what happens to dx? So dx, when you fix a generic y, you see that the x part ranges from 0 all the way to this plane, actually to this line in the plane. We're only looking at the plane, and the most will be x. So here y is fixed. Oh, sorry, we can't say x goes from, so this dx integral, so the boundary shouldn't involve x in it. Okay, so x goes from 0 to y, and now in the inside we want to get the dz part, which means to find it you fix a typical point in the projection. So now your x and y is fixed. Where does z range? So it contains this vertical segment until it reaches the curve up there. So this will be from 0 all the way to that z equation, 4 minus y squared. And the function I integrate will go finally in here. There are no Jacobians involved in doing such things. So that will be one way of it, which equals if you did it the other way around. So this time, let's say we start with parameterizing the x first. So as x goes from 0 to 2, here is 2, y goes from, so let's put the x here, y goes from, you see that it's actually up to this point. So when you freeze your x, y goes from x until 2. That is your dy, and the dz part will be the same for the reason that you just fix a point in the xy plane. So xy dy z. So these two will give you the answer. Of course, if you only want to find the integral, you do one of them. The next type of question, question 38, although it also has a picture in it, but let's make it more difficult and say we don't have a picture to begin with. We want to rewrite this integral in 5 more ways. Any triple integral can be written in 6 ways because you go dx, d of the other parameter, d of the other, and it's a combinatorics question. You have 3 choices here. Once you make one choice here, you have 2 choices here, which either one can go with the initial one, and then the third one you don't have much choice, only one, and then you multiply. That's combinatorics mathematics 6. So if you have 3 colors for your t-shirt and 2 colors for your pants, you have 6 ways of combining them. So in order to answer such a question, we have to first get an understanding of the domain we're talking about here. And let's try to see what's happening. We have to read everything off the boundaries. F is irrelevant. Actually, we don't know what f is in this case. So this integral says as x goes from 0 to 1, as x goes from 0 to 1, so that will be here, z goes from 0 to 1 minus x squared. So we're looking at first the projection onto the xz plane. 1 minus x squared is a circle, of course, in this plane, and we don't care about that other side because we start, because x is limited to here. So when you freeze your x, z is this much, and once you fix your x and z, y goes from 0 to 1 minus x, so that will be like here. And 1 minus x, we see that is this line and this plane, in fact, right? Because we are in 3D. So that is the plane y equal 1 minus x. So the region we're looking at is part of the cylinder. So you have this cylinder in direction of y, but you cut it off with this plane. So I know my picture is gonna get messed up, but this plane cuts a part of it, so it won't be really cylindrical in that case. So somehow this cuts that. Okay, yeah, maybe this makes some sense. So this is, again, every time I see a piece of cake, I see these regions. You can imagine them as other favorite shapes that you have, a piece of a cheese or something. But anyway, this is the region we're looking at. Now, to rewrite them in different order, you start with a different projection. So this was projection onto the xz. Actually, I can just switch here. So what if I wanted to go dx dz and then dy? So let's see what happens. Equal. So where would be the range of z? If I look at my picture, z goes from 0 to 1, because here at the maximum z was 1 minus x squared, so 1. And when z goes from 1 to 0 to 1, what is the range of x? So x and z are related by z is equal 1 minus x squared. So x in terms of z will be 1 minus z root, and it's the positive side. So x will go from 0 to that, and the y part isn't changed. So what we did here was only in the projection switch between dx and dz. So we did the same plane projection. So this gives us the 2 ways of rewriting the integral when you look at the projection onto the xz first. Now let's look at the projections onto the xy plane, which means that my innermost integral will be dz and my outermost will be dx dy. So let's do first dx dy, and then we will go and do dy dx. Okay, so what happens? First I'm doing the y part. If this formula is 1 minus x, then this point will be at 1, and this is at 1. So y goes from 0 to 1. And when I fixed my y, let me use green here. When I fix a y, then z ranges from, the x ranges from 0 to x solved here will be 1 minus y. So I hope you can read that green easily there. So that will be it. And then z goes from 0 to 1 minus x squared. And then f of x, y, z dz. So that will be that. Let me do this. This time, again, I will keep the dz fixed. And now I want to go dy dx. That means I'm looking at the projection onto the xy plane again, but this time I'm going to do x first. So x goes from 0 to 1. And when I fix my x, look at my picture. I'm going to draw this thing. So when I fix my x, where does y range? So y goes from 0 to 1 minus x. And finally, in the inside, z goes from 0 to 1 minus x squared. F of x, y, z. The reason we don't see any y in these upper borders is because the formula z equal 1 minus x squared is a cylinder and actually doesn't depend on y. So if this depended on y, definitely we would see some dependence there as well. Because this is exactly what that formula is we plug in. If it had y, we would also use that. Now let's do the projection onto the yz. So yz will give us the two remaining inequalities. So, and then dzy, and the interiors will be dx. Yeah, so I think this method of looking at which projection we do first is a methodical way of going about it and never missing any orientation or redoing the same thing twice. So when I look at my y and z projection, do I see a rectangle? That's the question. In fact, I do, right? So the height here doesn't change because it's always up to this point and it's independent of the y. Okay, so let's see. First I'm gonna do z. So z goes from 0 to 1. What happens to y value? Actually, it's not a rectangle according to my calculation. So my picture, that means, is a bit misleading to myself at least. So when z goes from 0 to 1, y goes from 0, sorry, wait a second. Is it a rectangle after all? Is y limited by z? Y goes... It is not actually. So when I look at the projection here, what does that mean? That means x equal to 0, and that means z is equal to 1 at the top. So the top, so it's not limited. So this will be from 0 to 1. And when I pick now a point here in the x and y and z plane, what is the range of the x? The range of dx will be from 0 to 1 minus y. And now this will be f of x, y, and z. Now let's do the other one. So because we were looking at the rectangle, y goes from 0 to 1, z goes from 0 to 1, and then x goes from 0 to 1 minus y as before. So 1, 2, 3, 4, 5, and 6 ways of rewriting the same integral. You can see that although mathematically they are equal, some calculations might be much easier than the others. Actually, there are interesting examples where you can do an integral only by switching to the other order and something magical happens. For example, we know that it's not easy to find an antiderivative to this. In fact, antiderivative to this isn't even an elementary function, so it's proven that there is no combination of these basic functions that we know, trig, ln, e, and anything, so that its a derivative will be this. But then when you're doing double or triple integrals, all of a sudden by reordering these, you obtain some extra x here, and now this becomes a u substitution because this becomes basically 1/2 e to the u du, which then you find antiderivative to. So there are practical and theoretical significance to this ability to rewrite the integral with different variable coming first. So please go back to the book and find other exercises and challenge yourselves to graphing them and visualizing the regions. Good luck.